Another design is known as parametric design. Now, the idea is to vary some feature of your stimuli parametrically. For example, you might take a sound and you might make it stronger and stronger and louder and louder and louder and louder. And the rationale behind it is that as you make it louder and louder and louder and louder, whatever part of the brain is important for processing sound might also respond more and more and more and more. So you would present stimuli at different loudness, and if there's any part of the brain that has a bold signal that scales with the loudness, then that part of the brain must be important for processing your stimuli. The typical example would be visual contrast. So you might show an image, but it's very dim, and then you slowly increase the contrast of that visual stimulus. And then you look for parts of the brain that have a bold response that also slowly increases as the contrast gets stronger and stronger. Now, this approach doesn't assume pure insertion, but assumes pure modulation. The idea with pure modulation is that as you make the feature of the stimulus stronger and stronger, for example, as you make a sound louder and louder and louder, your brain just does more processing. So your brain increases quantitatively the amount of processing, but it doesn't change from a qualitative point of view what your brain does. So whether it's a very soft sound or a very loud sound, your brain does the same. It just does more of it for the louder compared to the softer sound. Okay, so this is pure modulation. It also assumes, in a sense, that there is some kind of magnitude that you can define across levels. So you can say, well, from level A to level B, it's 20% stronger, and from B to C, it's another 20% stronger, et cetera, so that you can look in the brain and you can say what parts of the brain scale with this 20% stronger, 20% stronger, 20% stronger. Let me show you an example. So Boynton and colleagues in '96 did exactly this. They used visual contrast, and it was a simple a checkerboard type pattern. And what they did is that they just changed the strength of the contrast of the checkerboard. And what you're seeing down here is on the x-axis, the strength of the contrast, and on the y-axis, the strength of the bold response. And so what you see is exactly as you'd expect, this linear trend where the greater the contrast in this particular part of the brain, the greater the bold response. So this means that this part of the brain really cares about contrast, because the greater the contrast, the greater the response. And the two scale with each other. Now, it's not always that easy, however. Here's another typical type of parametric design that is used all the time in the context of working memory. The task, if you've never encountered it, is known as an n-back task, and it goes like this. So again, you're my participant. In the zero-back condition, I just tell you every time so these are the little screens that you're inside the MRI machine, and I just show screens. There's a circle and a little dot appears. Okay. In the zero-back condition, your job is to press a button every time the dot is in the north position, is here. So you look at this, you don't do anything. You look at this, don't do anything. You look at this, match, click. You look at this, don't do anything. You look at this, don't do anything. Look at this, match, click. Right. Now this is the zero back. Now let's do the one back. Now your job is to press a button every time the position of the dot matches the position of the dot in the screen before. That's why it's called a one back task. You have to match the position of the dot to the screen you saw a moment ago. So for example, so you look at the second one, doesn't match the first one, so nothing. Look at the third one, it doesn't match the one before, so nothing. Look at the fourth one, oh, this matches the screen I just saw a moment ago, click. And so it's one back because you're comparing the screen to the one just before. And of course, you can see how we can turn this into a parametric design, because now we can do a two back. And the two back, what you do is you take a screen, and the question is, does this screen, does the position of the dot here match the position of the dot two screens ago? Right, so here it's a match because this one matched that one. And then you go to the next and you say, well, does this one match the position of the dot two screens ago? And what you have to notice is that, for example, when I'm here, I have to keep in mind two screens. I have to keep in mind the two screens ago because that's the one I'm comparing to what I'm looking at now. But I also have to keep in mind this one here because I'll have to compare this one here to the next screen. And once I'm here, I have to compare this one here to two screens before while holding in mind where this one was, so that when I go to the next one, et cetera, et cetera, et cetera. And you can do the three back task. And the three back task, same thing, but you're looking at three screens before. So for example, when you're here, you are comparing the position of the dot here to the position of the dot three screens ago. And while you're doing that, you got to keep in mind the two screens ago and the one screen ago, because you're going to use them in the next trial. When this one shows up, you need to compare it to 1, 2, 3 screens ago. And in the meanwhile, you have to keep in mind the two screens in between and keep them in the right order, et cetera, et cetera. Now, when you look at the bold response to this, which is what I'm showing here, so here you're seeing on the x-axis, whether it's a 0, 1, 2, or 3 back. And on the y-axis, you are seeing the strength of the signal change with respect to baseline, to just looking at the blank screen. Turns out, it's not quite as linear as the contrast. In fact, it really looks like 0 back and 1 back are one type of task, and 2 back and 3 back are just qualitatively different. It's not sort of a linear increase. It really looks like it's just a different beast of a task. So parametric designs are wonderful, but they're also complex at times because it's not always easy to find a way to modulate whatever you care about in a way that makes it sort of quantitatively different, but not qualitatively different. Another frequently used design is known as selective attention. Now, this design is particularly interesting because the stimuli that you are providing to your participants are the same under task A and task B. What changes between task A and task B is what your participants attend to. Let me give you an example. So this is a stimulus I've used for a study we've published a number of years ago now. And as you can notice, there are two things portrayed in this image. And so what we did is task A, and in fact, I'll ask you to be my participant. Task A is look at the stimulus and please focus on the face and do it. Look at the face. And you might have the sense that in your mind, what you're seeing is a face. Of course, there's a house there too, but you are focusing your attention on the face, and the house kind of feels like it goes in the background. And then task B would be the reverse. And I'll ask you to do it. Focus, look at the image, and now focus on the house. And you might get a sense that even though the face is still there, the center of what is in your mind, what is in your conscious perception is the house. And see, the beauty of this design is that what is hitting your retina is exactly the same under task A and task B. So the stimuli are perfectly matched. What is different is what you do with them. And typically this type of design is meant to have the participant sort of focus on a specific feature of the stimuli, in this case, a different object. Now, selective attention designs do also have assumptions, and principally, they assume that the cognitive processes that you're interested in can be modified by attention. so that you can modify, for example, object perception and object recognition using attention. They also assume that the features that you're not attending to, so for example, when you're focusing on the face, that the features of the house don't quite creep in very much. So in a sense, it does assume that when you attend to something, you're really bringing into the focus of your mind one particular feature of the display, in our case, for example, the face, and the other stuff is really kind of getting ignored and pushed away. Okay, so you are making these assumptions if you use this design. Finally, the last design I want to cover is known as priming or adaptation design. And the idea in these designs is to present some kind of stimulus or some kind of feature multiple times back to back. And the idea is that if you present something multiple times back to back, the neural response to the second presentation is usually decreased compared to the first one. So the inference would be that if I show you a given stimulus or some kind of feature 2 times back to back, if some part of the brain responds a little bit less the second time around, that must mean that that part of the brain is important or sensitive to that stimulus or feature. And you can use this sometimes in very clever ways. In fact, let me give you an example. For a number of years, there's been a raging war in cognitive neuroscience, or a raging war in cognitive neuroscience. And the question was all about this little region right here in the temporal cortex, which is known as the fusiform word form area. And the debate was whether this region is a visual area, meaning it responds to the lines that make up words, or whether it's a semantic area, meaning it responds to the meaning of the words. And see, these two things are difficult to disentangle, because if I show you the lines that make up a certain word, you will automatically trigger the semantic meaning of that word. And it's difficult to tease apart those two aspects because they're so tightly linked. And it took a priming and adaptation design to answer this question. So let me show you this particularly clever experiment by Stanislas Dehaene and colleagues. And it went something like this. Imagine you're the participant, you're inside the MRI machine. And the first thing you see in any given trial is a mask. So these little squares are just a mask meant to occupy your visual cortex. And I show this to you for 271 milliseconds. Then I change the mask a little bit so it flickers. And for 29 milliseconds, you see a different mask. Then, and this is the crucial part, I flash very quickly a word. And I flash it for only 29 milliseconds, which is typically too little for you to consciously perceive it. Some parts of your brain will respond to it. So your brain, in a sense, will respond to it, but you consciously will probably not see it. And then right after those 29 milliseconds, I show another mask. This is just meant to prevent after effects, so that that word cannot linger in your mind as an after effect. And so you've seen a mask, you've seen some sort of jumbled lines, then I flash super quickly a word, and then I show a word for 500 milliseconds. And this last word, you can detect. And here's the manipulation. Sometimes, as you can see here, the two words are different. And not only sometimes they're different, so flower versus radio. Sometimes they're different, but they have the same font. See, they're both uppercase. Other times, not only they're different words, but they're also in different fonts. One is uppercase and one is lowercase. So this would be a different word trial, and you can either have same font or different font. As compared to that, you can have a same word trial. And the trial worked exactly in the same way, except the final word was always the same as the prime word. Here too, sometimes they came exactly in the same font. Other times it was the same word, but came in different font. And you will notice that this is the crucial manipulation, because the same word, but the lines are different. So let's see how this goes. So what I'm plotting here is the x-axis is just a little different categories. So whether you will see whether it's the same font is on the left, if it's the different font is on the right. And we will get in black, the black bars indicate that it's the same word, the prime and the final word. And the white bar indicates that the prime and the final word are different words. So first, there are two conditions where the word is different, and so DW, and the font is different. So that would be this condition right here. Different word, different font. So flower, uppercase, and radio, lowercase. Condition number two is different word, same font. So that would be this when radio is written uppercase. And when you do these two, there's no reason to expect any priming, because it's different lines, whether it's the word flower, right? The word, whether it's uppercase or lowercase, sorry, whether radio is uppercase or lowercase, it's different lines than the word flower. And in these two cases, we get this much response from the fusiform area. Third condition, same word, same font. So that would be uppercase radio as the prime and uppercase radio as the final word. What do you expect to see here? Well, whether the fusiform is a visual area or a semantic area, these two words, when they're both uppercase, they mean the same thing. They have the same font. So it's the exact same line. So regardless of which theory you believe, we have to see priming in this condition. And that's exactly what we see. So the response to this word, to the second word, when it's uppercase, when it matches the prime word and it's also uppercase, shows priming compared to when the words are different. So the difference between when the two words are different and this, that is priming. The fact that when you see a second word that is the same as the first and in the same font, you get a decreased response. That is the definition of priming. The key manipulation is the third condition. And that is what you're seeing here. It's the same word, radio and radio, but one is in uppercase and one is in lowercase. So visually, they're different. And see, here is where the whole study plays out. If the fusiform is a visual area, then the lines that make up this word and that word are different. So we ought to see no priming. If instead the fusiform word form area is a semantic area, then these two, regardless of their font, they mean the same, and so we should see priming. See, it's a very clever design that allows teasing apart these two aspects. Lo and behold, we do see priming. So it turns out the fusiform word for the area, thanks to this really clever priming adaptation design, actually was shown to be a semantic area. Now, of course, here too, we're making some assumptions. And in particular, this type of task requires a version of the pure modulation assumption. In fact, it almost requires the reverse of the pure modulation. It assumes that processing of whatever is the relevant feature is reduced the second time you're exposed to it, but overall, it's the same thing. In other words, when you see a second stimulus, sure, you process it, sort of the strength of the response is quantitatively decreased, but the response qualitatively is the same. So it didn't change what you're doing, it just changed a little bit of how much of it you are doing.